Hello everybody, Mr. Mark with you, and in this video we're going to talk about heating, cooling, and specific heat. A lot of these topics are new this year in 2024 to AEP Physics 2, and if there are a few clarifications we need to make about things that we've previously discussed. So a lot of important information in this particular video lesson. So first, let's talk about the words heating and cooling. Previously, we've talked about energy transfer between two objects or systems via things like conduction, convection, and radiation. And energy is transferred thermodynamically between systems when they are different temperatures. So different temperatures is the key thing there. So when we say heating, we're referring to the process of transferring energy into an object or a system. Cooling is the inverse of that. You transfer energy out of the object or system. And so heating and cooling are verbs, and it's important to remember that. Energy is still the thing that's being transferred between objects or systems. So let's take a real simple picture. We have object A, a cylinder, which is hot, high temperature, 400 Kelvin, and a cube, B, which is cold at a temperature of 300 Kelvin. So that's a pretty significant difference of 100 degrees between the two objects. If we place them in contact with each other, they're going to transfer energy. The net flow of energy is going to be from the cylinder into the cube because the cylinder is at a higher temperature than the cube. And so we would say that energy is transferred into the cube by heating, energy is transferred away from the cylinder by cooling. We do need to be careful with those words. Those are action words. Heating and cooling mean transfer of energy. And so in the past, we may have used the word heat for that energy that is being transferred from one thing to another. And because that word gets used ambiguously, gets used in a lot of different contexts for a lot of different reasons, we've kind of just decided that in AP Physics 2, we're not going to use that term. We're going to talk about heating and cooling as processes and just refer to the energy as energy. It's just energy is being transferred, kinetic energy. And so when we look at the cube from our example, we may say that heat is added to the cube, but that's really not the best way to say that. So we're going to try to avoid using a term like that. And we're going to say that energy is added to the cube by heating. That means the net flow of energy is into the cube. That's a little bit more precise way of saying it without relying on the word heat, which is really used in a lot of different contexts differently. So we're going to try to stick to heating and cooling as verb. So we know from previously that over time, the rate at which energy is exchanged is going to decrease as the two temperatures get closer and closer together. So initially, the heat's going to be or heating is going to occur rapidly. Almost did it myself there. And then over time, as the temperatures become closer and closer together, the rate of energy transfer will decrease. And so that's the Q over delta T equals Ka delta T over L relationship that we've learned previously. So eventually, the two objects are going to reach the same temperature. There will be no net transfer of energy anymore. So heating and cooling will stop. Those processes will stop. And the two objects will be in thermal equilibrium. So today's question, what if we wanted to predict the final temperature of those two objects? How could we figure out where they're going to meet? Like what final temperature will they have? So let's talk about the factors that affect the amount of energy transferred during a heating and cooling process. The first factor is going to be the mass of the object, just how big it is. More massive objects have more particles that can transfer energy with each other. The second factor is going to be the temperature change of the objects. So we have to be a little bit careful. Here, delta T represents the temperature change of one of those two objects. So kind of obviously, the greater the temperature change, then the more energy was transferred into that object or system. And then the third factor is just the properties of the object itself. And most of the time, when we in physics refer to properties of objects, most of those things we just leave up to the chemist to figure out. we just kind of want to boil that down to a single number. And so that single number is called the specific heat of the object, and it has the symbol C. On the AP Physics 2 formula chart, they use the symbol lowercase c. You also see it written as a capital C, just depending on the source. We're going to stick with lowercase c because that's what you're going to see on your equation sheet. So, kind of combining those three factors together, the amount of energy transferred, which is Q, Q is the energy transferred by heating or cooling, is just the product of those three factors, the mass, the specific heat, and temperature change. So let's discuss the idea of specific heat just a little bit. The specific heat of a object or system depends on many factors. The state of matter is one of those factors, and it's kind of worth knowing that when you change the state of matter, you change the specific heat. So, for example, liquid water has a higher specific heat than solid ice. In general, metals have very low specific heats, which is why they're useful for making things like pans and grills, things like that we cook with. It takes just a little bit of energy to change the temperature of a metal pan, which makes it useful for cooking. You want it to be hot, you want its temperature to change easily. Conversely, water, liquid water in particular, has a very high specific heat. So water is useful for cooling things down. It can absorb a lot of energy by heating without a really large temperature change. It's a temperature moderator in a lot of situations. So we use it to cool your car's engine. It cools the land near a coast. So when you go down to the beach, the temperature doesn't change as much during the day because you're close to a large body of water. So coastal areas, the temperature is usually more moderate than further inland. It's also why your swimming pool stays cold well into the spring, even as the weather starts to heat up. So it's kind of worth knowing that the specific heat of water in AP Physics anyway is 4,180 joules per kilogram per Kelvin. You can express it in a bunch of different units. If you're in chemistry class, you're probably going to do 4.18 joules per gram, sorry, gram, and then degree Kelvin. You can express that in a lot of different ways. And so, as always, as you transition back and forth between your different courses, just keep in mind that those numbers may have different units, different contexts. So one thing that's worth noting as you're sitting here in AP Physics 2 in high school is we do consider a simplified model of specific heat in which the specific heat of a given substance is more or less constant. And so we assume when we model that the specific heat doesn't change with factors like temperature, pressure, density, and things like that. And so one day later on, you may study how temperature changes the specific heat of an object. Like as it gets hotter, its properties change. But in AP Physics 2, we're not going to get into those factors. And so if we have a specific heat for an object, we have a number, that number is not going to change regardless of how the properties of the object changes along the way. And we'll assume that it's constant unless we're told differently. So let's go back to our example that we were working with earlier and kind of just pulling up some common hypothetical numbers. Let's figure out what the equilibrium temperature of our cylinder and cube would be. And so if we have our original temperature of our cylinder, 400 Kelvin, and a mass of 2 kilograms, quite a large cylinder, and let's just assume that this thing has a specific heat of 200 joules per kilogram degree Kelvin. So what that means is it would take 200 joules of energy added by heating to raise a 1 kilogram sample of this thing by 1 Kelvin degree. And then for the second thing, the cube, let's assume it's got a mass of 4 kilograms and a specific heat of 500 joules per kilogram degree Kelvin. And so I want you to kind of do is just kind of estimate like where's that equilibrium going to lie, just kind of briefly looking at those numbers and kind of thinking through those three factors that we just discussed. And so it's important to remember that energy is still conserved. So we have energy being transferred into the cube by heating, energy transferred from the cylinder by cooling. Those are the same energies. And so what's lost by one thing must be gained by the other. So the energy transferred from the cylinder by cooling has to be equal to the energy transferred into the cube by heating. If we call the energy transferred from the cylinder QA and into the cube QB, we can write that negative QA equals QB. And the negative sign is, of course, because the cylinder is losing energy. That energy is going out of the cylinder and into the cube. So, kind of setting up an equation, starting with that little fact, the energy is conserved. That is an energy conservation statement right there. Then kind of substituting in that Q is mc delta T, as we just kind of got done doing. Then we can go, wait a minute, we want the final equilibrium temperature for both of these things. That equilibrium temperature has to be the same. So if we call that TF, we can expand the delta T terms to be TF minus that original temperature. And so now we end up with an equation like this. And now we have some algebra to do. What we might do is kind of get rid of those parentheses by distributing the MC terms to both parts of, or both terms rather, inside the parentheses. So just doing some distributing gets rid of those parentheses. And then the next algebra step here will be just to kind of group the like terms. So everything that's got a TF in it, I'm going to move to the right side. So add the first term to both sides. And then everything that doesn't, I'm going to move to the left side. So basically add the left or the last term to both sides. Then I can kind of factor out the TF. So kind of undo that distribution step that we did earlier. And then even though it kind of looks yucky, really all I'm doing now is just dividing by a single thing. That term that's in parentheses, TF times all that stuff in parentheses. I'm just going to divide by all that stuff in parentheses to get EF by itself. So some little bit of algebra there. It looks worse than it is because you got a bunch of terms running around. You got a lot of letters. But we're distributing, rearranging to combine like terms, and then factoring and dividing. It's kind of going back to where our numbers were. Substituting our numbers again looks yucky because there's a lot of them. But all those numbers, when you do the arithmetic, boil down to 317 Kelvin. And the easiest way to think about the units here is just to look at the things that are in the numerator. You have kelvins, kilograms, and then joules per kilogram of Kelvin. And then look at the things in the denominator. You have everything that we just listed except for the Kelvin term. And so your answer must be in Kelvin. And when you kind of stop and think about it, it should make sense, number one, that temperature is in between those two original temperatures. And then it should also make sense that it's closer to the original temperature of the cube for two reasons. The cube has more mass, and so it's going to take more energy to change its temperature and a higher specific heat. Both of those factors will lead to the cube being more difficult to change its temperature than the cylinder. So let's talk about our key takeaways and close this thing out. The two verbs that we learned today, heating and cooling. Heating is a transfer of energy into a system. Cooling is the transfer energy out of a system. We can quantify that with the little Q equals mc delta T equation that we learned. Energy is exchanged between two objects or systems until they are in equilibrium. When they are in equilibrium, that means they have the same temperature, and the net transfer of heat will go, I almost said it again, the net transfer of energy will be zero at that point. And then the amount of energy to transfer it on those three factors that we talked about earlier, the mass, temperature change, and then the properties of the system, which are quantified in that Q equals mc delta T equation. So this is our first basic introduction. Of course, we'll work with it in class. We'll actually do a lab with this one. We'll measure the specific heat of something. Usually we use a metal because they're easier. We'll do that during our class time together. I will see you then. Until then, ta-ta.